Okay, so yes. So take or leave that correction on how to define resonance effects. And then for the practice question, we're talking about structure and the relationship with acidity, right? Structure determines function, the strength of your acid based on the structure of your acid. And then we talked about excess strong acid, strong base problems, which I'm also going to clarify in a second. But for this problem, what did we say was the stronger acid and why? Oh, Joy? Why are you laughing? Why is that funny? Huh? Oh, that was a book problem. Okay. Okay, acid 1 or acid 2? Okay, why acid 1?
Because reticence gives it stability.
Okay, so the resonance effect stabilizes the conjugate. Formed. And where is the resonance coming from?
The bond.
Which bond?
The double bond.
Okay. The double bond really translates when you draw resonance to 1.5 bond across the molecule. So, great. Awesome. Warm up. Study this table of binary acids. Rank the following compounds below from strongest to weakest. Give a complete explanation for your reasoning. Obviously, that was a very squished. What did we say was the weakest acid? Huh? Methane? That would be a great one to put. Methane is non-polar. It's literally known for being non-polar. It's a hydrocarbon. So and there isn't that many electrons involved because you're only doing it H bonding, which means you only have 2 electrons being shared throughout the molecule for each H. So it's just a low electron dense anyway compound. Yeah.
That's the weakest one, right?
Mm-hmm.
That's the strongest.
Okay. What was the strongest? Yeah, Megan. Yeah, it's wait, the most electronegative? I think I get what you're trying to say. Charlie, you want to modify?
I think we're looking at electronegativities. It would be HCl, which is the most electronegative. But the problem with that is that our acid table ranks high above.
So you don't have exactly a straightforward problem here. You have to consider the size, the bond length between your H proton and the remaining conjugate base. If it's a binary acid, the remaining conjugate base, okay, is just the halide or halogen alone. But then for these ones, you have 2 protons, H2Se, and you have to consider here, you're comparing the S versus the Se. Which one's more electronegative? Which one's a better electron withdrawing group? I personally would put all of the binary acids somewhere in the middle. And I would put these SES containing closer to the top, but I also think that this is just a really hard thought question. Because when you look at the actual data, right? The actual data can actually, that sounds silly. The actual data can defy the trends, as we know. Periodic table, you do have elements that have masses less than what you would think they'd have despite their position on the periodic table. So in the end, they will almost always give you the data, or they will give you a pretty straightforward question where you're kind of comparing one thing has changed. This was an argument-based question. So if you can create an argument, okay, that follows the concept of you can talk about electron withdrawing and you can talk about increase in bond length, increase in acidity, and you can make that argument. That was the point of this practice question. Yes. Oh, you're not raising your hand. You're just holding a water bottle. Weird. Okay. So is it okay if we leave it at that? Here's my note to you. You need to consider in your argument, can you talk about increase in bond strength means decrease in acid strength? Okay. And then can you talk about for a compound such as Se and S, can you talk about increase in electronegativity, increase in acidity? There are different rules that you apply with binary. Binary acids, you focus on these rules. These rules matter with binary acids. When you have non-binary, you kind of focus on these rules. Okay. So for good there, I want to go back to the problems that we ended with yesterday. So first of all, hopefully having the process written out to the side helped. Okay. 2, here's why both of these ways are correct. The first method gave you the conceptual understanding of how we get acid from excess OH present in water. The first method revealed that you completely used up, neutralized the acid, and therefore the only acid remaining in solution is the water itself for the excess base to react with. One second, I'm trying to pause this. Help me. Why isn't it pausing? Oh, does anyone have a question about how we derived that part highlighted in pink, the first method, to why we can use it, the POH, pH, their logarithmic derived method in the second one? It's accomplishing the same thing. It's just one level of math different. Okay. Frankie, could you get your head up? Okay. I simply would just use this method personally. I just wouldn't waste your time on the KW method unless you have to. And that would be in a ice table problem, but this is a strong acid, strong base, excess ion problem. Just go straight from whatever is the excess, figure out its PaOH or pH, and then relate POH and pH from there. Yes.
Can you still use pH and pH if it's not in water? Because then you wouldn't.
You almost never get an acid-base question that's not in water, because the acid technically is an ionic compound in aqueous solution. Yes.
So do we need to know both of them?
I would focus on the second method because the first method is the conceptual understanding of the second method. It's where we get the second method from. Okay. So that being said, try the next problem and I give you a flow already. Okay, so you want to check for dilution. So you got to account for dilution in your calculations. And you're going to find that H plus is equal to 0.2 molar times, here's what you need to account for. You get 2 H's for every 1 H2SO4. And then you go back to the standard of times the ratio of the milliliters that you started with over the combined volume. And you should have gotten a value of like 0.1333 molar, something along that line. For OH, it's pretty standard. It's a 1-to-1 ratio of production from NaOH. So you're just going to get 0.4 molar times the ratio of the milliliters, the volume. Okay, and it becomes 0.2667. Okay, that's step 1, find diluted values. Now what you're going to do is calculate for excess. So obviously you're going to have more OH. So you're going to plug into the OH minus excess. Hold on. It's, you write it like extra small. Excess is equal to 0.2667 minus 0.1333. And that gets you a value of 0.875. Approximately, if you, depending on where you stopped on your decimals. I don't really know where you stopped. Then what we're going to do is we're going to
0.13, you know? The math is not math.
oh, sorry. I was reading in the next part of the problem. Sorry. Sorry, I was reading the next part of the problem. Thanks. Okay, so now what you're gonna do is you're gonna plug it in. You can decide to do it either way. You can decide to use the conceptual KW. I mean, I wouldn't, but you can. Or you can use the PHPOH method. I think either one's going to get you the same answer. I tested it with several problems yesterday, so it really will get you the same answer. Okay. But I'm just going to stick it into pH equals 14 minus POH because we are being asked what is the pH of the solution. So what you're going to get is that it's equal to 14 minus negative log of 0.1333, which would have gotten you 0.875. And that means you get a pH equal to 13.125. And it is 3 sig figs based on the sig figs after the decimal. Given that you were, all your known data was 3 or 4 sig figs. And that would be your answer. And it makes sense because you know that you have excess OH. So you would never expect your pH to be anything less than like at least 8, right? Like it's got to be higher than 7. So feeling good? Great. Do you want to do the next problem? No? Yes, go for it. What you should have done is for this sample problem, you should have noticed that you were given the initial pH, which means you were given initial concentration. Okay. So you should have to solve for the initial concentration of your acid and your base. You should have raised your pH values that you were given to a negative power and 10 base raised to the pH. Okay, and you should have gotten then a value of 0.01, well, sig figs, 0 molar. And then for OH minus, you should have gotten that you had to, well, you had to first solve, given the pH, you can solve for OH. So here you would use POH equals 14 minus pH, which tells me that my POH is 2. So then I do the concentration of my OH minus is 10 raised to the POH. And I would have gotten that I have also a value of 0.010 molar. So now what you have to recognize is that you are diluted. So, you would do dilution. So this is initial, but you now need to figure out diluted. So you should have gone for your diluted values. H plus is 0.007. OH minus should have been found as 0.0030 molar. And then you find the excess. And the excess H3O plus is 0.0040 molar. And then you just plug this in to your pH. Is equal to negative log of H3O plus excess, which is should be equal to 2.40. 2.400, but the pH that you're given a pH of 12, and this only has 2 sig figs. Yeah. So this is why. What are you doing? Is a bird in the class?
Yeah.
Oh my God, Nandez. Go away. Okay. So now we're going to move on to Ka, your pre-lecture material, calculating Ka, Kb, weak acid, weak base equilibria. There are 6 types of problems that I'm going to introduce today, but 3 of them are aligned. So what you're really getting is 3 types of problems, one from the Ka perspective, one from the Kb perspective. All you're doing is you're learning 3 methods and you're flipping for Kb. But we're going to go through 6 types together. So last night you watched a pre-lecture on Ka and Kb. It is exactly K equilibrium just for an acid and a base, a weak acid, weak base. That's all it is. It's just a specific type of K equilibrium problem. Okay. Out of curiosity, when you look at the Ka values for this problem, predict whether reactants or products will be favored in the reaction between HCN and HCO3. I made a note up here that equilibrium always favors the reaction direction of the stronger acid base form, making, of course, weaker conjugate acid base forms. So by the way, Julian, this goes back to the workbook question 1 that I went over yesterday. So, wow, gee willikers. So what did we say for this one between the HCN and HCO3, which would be favored? HCN, you say?
Wait, it's more like maybe the way that we want the way that forms it.
It always favors the side where your initial reactant, your relative reactant is the stronger acid or base.
You see it as a stronger acid. We want that. HCN is stronger acid. Favoring the HCN.
Does anyone want to confidently explain?
It says that it's stronger.
Okay. So you say HCN is this side that'll be favored because it's a stronger acid. Okay.
Right now becomes H2CO3. So
Mhm.
we're supposed to compare is whether the acid in the forward direction versus the conjugate acid in the reverse direction.
So the acid form of HCO3, yeah, you're supposed to be
So
comparing.
when you compare H2CO3 and HCN, H2CO3 is a stronger acid. So it's going to proceed more in the reverse direction in favor of the reactants.
So for this problem, and I probably misspoke it when I was trying to just have you guys try it out, is you're comparing this acid and this conjugate acid, and which is the better acid, and that tells you which side of the equilibrium is favored. So H2CO3 has a higher Ka value, which means the direction favored is the reverse, essentially. It's a stronger acid. Okay. So how about the next one? And I would start by writing the equilibria between the two. Figure out what are your relative acids that you're comparing. Can I remove the, oh, sorry. Does anyone have a response? Yeah, Keaton?
Well, H2SO4 is a really strong acid. So you would want to go the opposite direction, so it would favor the
H2SO4 is a really strong when it reacts with HC2O4. Oh, well, we're putting it in terms of the reaction with HC2O4. You're right, though. H2SO4 would be it, but when we react it with HC2O4, it's a polyprotic, so it's actually doing the next equilibrium, the next round of deprotonation.
We're getting H2CO.
Yeah. So mhm. So here again, it's the same thing where you have a higher Ka, so you're the stronger acid, so the reverse is going to be favored. Oh, remember that thing about polyprotic acids? Every round of deprotonation, you become a worse acid. Yeah.
How did you know that H is a 4 minus?
You had to compare the Ka values of HC2O4 and HSO4. Yes.
How do you know it's that instead of H2SO4?
Yeah, you know it's good. You just had to compare the values of the Ka and they would give it to you. So you would know that HSO4 is a better acid than HC2O4 minus. So that would be the one that would be deprotonated. But then you compare the relative acids of the acid and the conjugate acid present. And then you'd see, because they're each on different sides, and then you see which one would be the driving acid. Mhm. So in here, it's all about like, look at the table to determine who's the acid in the beginning. Okay, so let's move on to our Ka problems. Okay, we have 3 types of problems. They're just going to repeat essentially in steps with when we talk about KB problems. You're going to see the same type of 3 problems that you can encounter. The biggest thing is that we have to account for the fact that we have partial ionization, and partial ionization makes things a lot more complicated because now you have to use ice tables, right? When you do any type of calculation. So we already know that things are in equilibrium. That means you're using ice tables. The general equation, and I think I've already written this above, but just so that you know, this is the general equation for a weak acid, how we derive the Ka expression. Notice we isolate it with its reaction to water so that we're not doing a neutralization here. We're just trying to define the Ka alone, okay? And its conjugate. And of course, that means your Ka expression. I think I did this in the lecture, right? Okay, so I'm just gonna leave it at Ka expression accordingly. You plug in. Okay, problem type 1 is you calculate H3O plus at equilibrium from a given Ka and initial HA. This should already sound very familiar from the other KEQ problems. It's now just in the context of acid. So what you have is you have an initial HA, okay? So it's obviously the prepared solution. You have to use an ice table, and your goal in these problems is to find the equilibrium values, the values at equilibrium concentrations. If you're given a polyprotic, okay, your first ionization or deprotonation is strongest, so it defines the overall Ka for that acid, okay, when you're given problems like that. And then we also have a percent ionization trick that we have to keep in mind when we're doing these, is that if your initial concentration of acid is 1,000 times greater than your, God, what was that? Than your Ka of the acid, we can assume change in initial concentration negligible. Change in initial H3O, initial negligible. This simplifies a lot of calculations. Yeah. So AP tip, when you're doing these problems and you want to use the negligibility 5% ionization rule, you do have to show your work somehow. You can't just use it without mentioning it. You have to like make a comment of some sort or show the math that you did it and prove that it is 1,000 times greater, right? And that was a tip from an AP grader. So let's go through the process. I'm telling you right now, you do not have time to write the process. So here's what I'm going to say to you guys. If you are someone who does not struggle with the math, spend the time writing down the process. If you are someone who struggles with the math, write down the math with me, go back to the uploaded notes to figure out the process. I've already pre-written down all the process. So, and I will upload these notes at the end of class. So for this problem, you are given, okay, hydrogen sulfide is a poisonous flammable gas who's, oh yeah, this is how you get rotten egg smell. And it has a concentration as low as ppm. Okay, that's tiny. It also is a weak acid when dissolved in water. Calculate the pH of this hydrogen sulfide, and given that it is 0.0500 molar. So what you should do is you want to always start by writing the equilibrium reaction because you know you have to translate it anyway to an ice table. So you're going to add it to what water is always involved, right? Because we're isolating the acid behavior. And it's going to produce the following conjugates. Now, when you set up your ice table, that is way too small. We never include water. Okay. And you are told that you have a molarity of 0.05 initially. Well, obviously you don't make anything initially in terms of ions. So then what you do is you use your algebraic expressions, okay? You know that the change is going to be minus X plus X 1-to-1 molar ratio. So you're going to get a value of 0.05 minus X X, and X for your equilibrium. Now, the next thing you want to look at is, of course, the Ka, and it would be given to you. So for this, Ka is 9.1 times 10 to the negative 8th. When you now bring in the Ka, okay, you need to check if you can use the 5% ionization rule to simplify your math. And you'll notice that a 0.05 initial concentration, 0.05 initial concentration is far greater than the Ka. So you can use the 5% rule and say the X change in initial concentration of the acid is negligible. So that's why I put a little smiley face next to the process. So then what you do is you now plug in your algebraic expression, X squared, because it'd be HS minus times H3O plus, which I guess I can write out. Yeah. H plus times HS minus conjugate all over the concentration of H2S, which equals X squared all over 0.05. Okay, and then you get a value of X equals 6.74 times 10 to the negative 5th molarity. And now that isn't what you wanted though in the end, because in the end you wanted the pH. So now that you found the concentration and X is equal to the concentration of H plus. So you simply now just plug into pH equals negative log of H plus at equilibrium, EQ at equilibrium, and you get a value of 4.17. Okay. So try this one on your own. All right, so you guys, for this next problem, you were given Ka and Ha initial, and you had to calculate pH. If I were you, I would have made a shortcut. I would have said H meth plus H2O goes to deprotonated meth plus H3O plus. And of course, we don't care about water. So you were given that you have 0.5 of solution methanoic acid. And you were given, that's it. So you know you have 0 and 0. You had to go back into your notes to find the Ka value, or you just searched it for methanoic. So what did you get? What was the Ka value for methanoic acid? Okay, so you are 1,000 times greater. You are pretty safe to use the negligibility. You're close, but you are 3 powers, right? 3. Yeah, you're 3 powers. You're fine to use percent ionization. Negligibility is okay. All right. So what you would have gotten is this, right? And then you would have gotten 0.5 minus X, but obviously we are going to consider that negligible, and X. And you would have plugged it into your Ka expression. So your Ka expression, Juan Carlos, good to see you. Your Ka expression, right, is the constant that is derived from essentially multiplying how much ion production you make. So your Ka is really just a measure of your ion production. So then you plug it into your ion production equilibrium expression, Ka, and you get X squared all over 0.5. And what did you get for pH then when you solved for X? What was your pH? Okay, are we all in agreement? Awesome. Yes. When it's solution, yeah, because remember an acid is technically in some form of ionic compound in a sense. So it's always an aqueous solution. Also, water is the environment for every single acid-base reaction. All right, problem type 2. This is where you calculate the initial given the Ka and the pH. So here, your unknown X goes into initial. You're actually solving your X variable is your initial, and then you cannot ever, you can never, not ever. Oh, you know what I realized? Not ever shortens to never.
Wow.
You can never, okay, use the percent ionization trick because you don't know if the initial is 1,000 times greater. You can't make that assumption. So for this, again, if you are more of a process person, just write the process, figure out the numbers later, okay? But what you would do for this problem is you're told that you have benzoic acid, okay? And blah, 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 blah. What concentration of benzoic acid is required to produce a solution with a pH of 3.30? So if your pH is 3.30, this is your pH at equilibrium. So that means you can solve for your H3O plus at equilibrium. So you get 10 raised to the pH, which means that your H3O plus at equilibrium is 5.01 times 10 to the negative 4th molarity. Okay, and so then what you do is you write out the problem. If I were you, I would do H benzoic plus H2O. I wouldn't look it up. I would just go for it. And do benzoic conjugate plus H3O plus. And then I'd set up my ice table. And of course, I never include liquids. And I would say that my X is my initial starting amount. And so what I do know is I do know the equilibrium for my H3O. So I would simply plug in 5.01 times 10 to the negative 4th. Well, that tells me according to my stoichiometric ratios, I have gained 5.01 times 10 to the negative 4th, right? 5.01 times 10 to the negative 4th. Okay. And what that means is I can just use my stoichiometric relationships to calculate the change. Well, then that means I can calculate my equilibrium. Oh, my equilibrium for all of it. Okay, and it becomes X minus 5.01 times 10 to the negative 4th. Then I would have to be given my Ka value, which you would be given in the prompt. But if you looked it up on the table, it would be 6.5 times 10 to the negative 5th. This is my ion concentration of conjugate times acid produced. This is basically just my ion product for an acid reaction. Okay, my Ka value. So then I now plug in to this expression what I know to be my equilibrium values. So it's 5.01 times 10 to the negative 4th, squared it, because it's the two products squared, the two ions squared times one another, and they're the same, all over X minus 5.01 times 10 to the negative 4th. And remember, I can never use 5% assumption because I don't know. I just don't know if it is negligible or not. I can't make that assumption. And I would get then that X is equal to 4.4 times 10 to the negative 3. And this is a 2 sig fig answer because I was given only 2 sig figs, 2 digits after the pH decimal. So that's why I'm only in 2 sig figs. And X is my concentration of benzoic acid. And that is the answer. Okay. So try the next one on your own. For this problem, okay, you follow the same process. You were given pH. So you know that the pH is going to give you, okay, the H3O plus at equilibrium. So if your pH equals 2.50, what you can figure out is the concentration of H3O plus at equilibrium. And that would equal, okay, what do you guys get? When you raise it to the 10 to the pH, what do you get for equilibrium? 3.16 times 10 to the negative third molarity. So then what you do is you set up your equation. So you're told that it's citric acid. So H citric acid, H plus. Protonated citric combines with water in an equilibrium to create citric conjugate. And you could add the minus to remind yourself, and H3O plus. You set up your ice table. I really hope some of you guys are getting something out of this. So you set your X initial equal, and then you ignore, because you don't get anything at first. And you plug in knowing that this, oh gee willikers. Okay. Copy. You know this is your equilibrium. So you know then you have a 1-to-1 ratio. So everything is going to change in accordance to this 1-to-1 ratio. Ay, ay, ay. Okay, and then I'm just going to add my pluses and minuses in accordance. And it becomes equilibrium of the H protonated citric acid is equal to X minus 3.16. Then you should have plugged it in to your Ka value, and your Ka value, I realize I should have left more room. What is your Ka value that you would have had to look up? Pardon me? 7.1 times 1. Thank you. I was like, what? So you're just going to simply plug in what you know. So it's 3.16 times 10 to the negative 3 squared. This is your ion concentration, right? The product of your ion concentration, the product of your ion formation. L over X minus 3.16 times 10 to the negative 3. What did you get for X, which is the concentration of your acid originally? What did you get? Molarity. So for the last problem, we have 6 minutes left in class. I'm going to get through one walkthrough, and then tomorrow, Monday, we'll open up with the practice problem. Yeah. Oh. Okay. There you go. So for the last problem, this is your dream problem. Here, you're just plugging and chugging all the way. You're calculating Ka given HA and pH. You're given your initial and your equilibrium concentrations. So for this one, what you would see is you're told that the pH of the solution was found to be 2.27. So pH, when you raise it, it tells you the acid concentration at equilibrium equals 10 to the negative pH. So you would get 10 to the negative 2.27, which by the way is 2 sig figs. And that's equal to a concentration of 5.37 times 10 to the negative 3 molarity. Okay, that is your equilibrium concentration. And then you just plug into your ice table. You know that aspirin is protonated theoretically, right? You start off with acidic protonated aspirin, AS. I'm just going to do that shorthand. and it reacts with water because we're isolating the acid behavior. And it's in equilibrium with its conjugate AS. And it produces H3O plus. You put in your ice table. This is the type of question you pray for. This is so easy. Okay. You're told initially from the practice problem, you have a 0.100 molar. That is from your practice problem given. Okay. And you know the liquid doesn't matter and you have nothing in the beginning. And then what you do is you just plug in, well, I also know my equilibrium, right? So you plug in accordingly, all your equilibrium changes. Okay. Ay, ay, ay. Do. It's tight. It's very tight. Okay. And then you simply plug into the Ka expression. -0.1 minus. Oh, that's tight. That's real tight. Okay. And then you plug into Ka expression, which is equal to the concentration of your H3O produced times the concentration of your conjugate base produced, raised to the respective powers, which is 1. It's a 1 to 1 to 1. All over the original, which is protonated aspirin. And when you plug that in, you should get a value of 3.0 times 10 to the -4th Ka, and it is 2 sig figs because your pH was a 2 sig fig pH, 2 digits after the decimal. This is the problem you hope for. So class ends in 4 minutes. You are welcome to power through the next one because I actually think you could. The slowest thing would probably be your handwriting. Does this feel good for everybody? It's a repeat of K equilibrium problems just with acid. Okay, I moved the schedule around. Monday, we will learn about KB instead of trying to give you a video this weekend to do it. So Monday, we will learn about KB. Your only homework tonight is to watch half of the AP question walkthrough that deals with KA, and then watch the indicator. Oh, no, that's it. It's just half of a problem video. That's all I asked for. Huh? Flipped, kind of, except what you have to do with all the KB problems is you have to relate KB to KA through KW. But yeah.
For these problems, when you found the